Welcome back. So we're talking about the Fourier transform and some of its neat properties that make it useful for solving partial differential equations and for function approximation. And now I'm going to tell you about two of my absolute favorite properties. The first one is really, really simple and very, very important, and I'll let you kind of work through and convince yourself that this is true, which is that the Fourier transform is a linear operator. So if I take the Fourier transform of some alpha f of x plus some beta g of x, this is going to equal alpha times the Fourier transform of f plus beta times the Fourier transform of g for all functions f and g and for all real numbers or complex numbers alpha and beta. Okay, so that's the definition, the property that needs to be satisfied for this Fourier transform operator to be a linear operator is that if I add two functions, if I take the Fourier transform of f plus g, it should just be the Fourier transform of f plus the Fourier transform of g, even if I scale them by some constant alpha and beta. Okay, so I'll let you work through this. You can literally take this expression, plug it in here, and it's very simple. I mean, these if you had alpha f plus beta g here, you could just split that up into two integrals. You could pop the alpha and the beta out, and you'd recover this property that simply. Okay, so that's easy. The next thing I'm going to tell you about is something called Parseval's Theorem, and I don't think this is the same Parseval from King Arthur's Knights of the Round Table. At least I don't think so. Parseval's Theorem, but this is an extremely, extremely useful theorem that allows us to use the Fourier transform for for function approximation. Okay, so I'm just going to write it out, and then I'm going to talk you through what this means. So what this tells you is that the integral from minus infinity to infinity of the absolute value of the Fourier transform of f squared d omega is equal to 2 pi times the integral from minus infinity to infinity of the absolute value of f of x squared dx. Okay? Now this might seem rather simple or rather dull, but this is actually quite a profound statement, and it's going to allow us to approximate these functions f. What this says is that this is kind of a representation of how much energy there is in this function f. This is kind of like the norm of f, okay? How big, how much energy, or, area squared under the curve of f there is. And that's similarly how much energy or area squared under the curve of the Fourier transform there is. And what this Parseval's theorem says is that these two integrals are equal up to a constant of 2 pi. Okay, so kind of the energy in f is directly proportional to how much energy is in its Fourier transform. Okay, I'm using the word energy to represent this norm here. Okay, and that's extremely, extremely useful, because what that means is that if there are some really, really small Fourier coefficients, if I Fourier transform f of x, and there are some really, really small Fourier coefficients, and I just ignore them, I zero them out, this integral won't change much. And the question is, if I zero out those small Fourier coefficients that are really, really negligible, maybe it changes f of x a lot. Maybe it has a big impact on my approximation of f. What this theorem says is that if there are Fourier coefficients that are negligibly small, and I remove them, I set them equal to 0, I truncate my Fourier series or Fourier transform and remove those almost 0 Fourier coefficients, because this integral doesn't change much, it tells me that I'm still capturing most of my function f of x. So if I truncate my small Fourier coefficients, I negligibly degrade my approximation of my function f of x. That's a super useful property. We're going to use that all the time when we write these Fourier transforms and we use these to approximate functions, is the fact that if there are small Fourier coefficients, I can ignore them and I'll still do a pretty good job of approximating my function f of x. Super useful. This is related to the fact that the Fourier transform is a unitary operator, which means essentially it preserves kind of distances between functions. If I had two functions f and g, in x coordinates and I Fourier transform them, they're going to have the same inner product in Fourier transform coordinates. Okay, that's another kind of subtle property of Parseval's theorem. Okay, super useful, really, really important for function approximation if we want to ignore small Fourier coefficients. Okay, thank you.